All right. Any questions before we get going? Okay. All right. So today's lecture is one last really fun graph algorithms lecture to kind of top off a few straight weeks of graph algorithms. So we'll look at two problems today called vertex cover and matchings. They'll turn out to be close related to some stuff we've already discussed. Okay, so, all right, the vertex cover problem. I give you an undirected graph, okay? And vertex cover means you choose a set of vertices so that you're taking at least one endpoint from every edge. Okay, so you're choosing vertices that cover the edges. Okay, so here then is an example of an undirected graph, and then so I'm going to ask you what's the minimum size vertex cover in this graph. I'll give you guys a minute to stare at it. It's a big graph. I counted that there's 21 vertices, so that would be an upper bound. Not sure. Maybe it's hard to do in your head. Anyone get 15? Maybe it's too hard to do in your head. Okay. What I'm going to do is then I'm going to just point at vertices. You tell me if I should include it in a vertex cover or not, and we'll just see how many we end up with. I think I drew too big of an example. That's okay. All right. Let's start with the top left. Should I put that in? No? Okay. I won't put that in. I'll put an X there to remind myself. Okay. How about here? So at this point, you do have to, because you have to make sure you take at least one endpoint from every edge. So if we say no to the first one, then this one now is forced. Okay. Okay. How about this? So arbitrary. Okay. No. Guess I'll go here. Yes or no? Either one's fine. Yes. Okay. I see some yeses. All right. Should I take this one? This one you actually have to because of this edge. You have to make sure you cover all the edges. All right, you guys want me to take this one? No? I'm just looking for like one head shake or nod among you guys. Okay. I don't know what the optimum solution for this is. Let's at least make sure we output a vertex cover though. I have some simpler examples coming up. All right, how about this one? This one you have to. Hopefully I haven't made a mistake yet. Okay, how about that vertex on the left? Yes, okay. How about this one? Oh, we have some controversy. I'll go with a no. Oh wait, but this one you have to actually, because if I did no, then I would leave out this edge. Okay, so this one I have to. Okay, next kind of row. How about this vertex? This one you have to cover that leftmost edge. This vertex, no. See a lot of no's. This vertex, this one you have to. What's next? All right, how about on the right? This vertex. Okay. Oh, this one you have to, because again, it's incident to one we've already skipped. What's next? Let's go here, bottom left. Yeah. Okay. Well, oh, we have to. How about this one? I actually don't have to, amazingly. How about this vertex on the right? No. Okay. Okay. How about sort of? I'll go on the bottom. Okay. Bottom left. Yes. You have to, I guess. How about here? The middle, near the bottom. Mostly nose. How about this one? This one you've got to. And this one, you also have to. Okay, so whatever that. The ones we've circled, ignore all the other purple scribblings, would hopefully be a vertex cover in the sense that we've taken at least one endpoint of every edge. It's not at all clear that we chose a particularly good vertex cover, but a vertex cover it is. Okay, so that's fine. That's just some. Okay, so here are maybe a couple much simpler examples. So on the left, out of these 5 vertices, these 2 are clearly optimal. Okay, and on the right, kind of this wheel, just choosing a middle vertex would be a vertex cover of size 1. So that would be much simpler examples. You could just eyeball and see that they're optimum solutions. So in general, the problem is to find the minimum cardinality vertex cover. Of course, we could put weights on the vertices and ask a weighted version of the question as well. Or if it's a decision problem, I'd also give you k and say, okay, can you find a vertex cover with k or fewer vertices? Okay. All right, so that's one of the 2 problems we'll look at. Oh, I guess I should point something out. So unlike spanning trees, but like some other problems, a minimal vertex cover is not necessarily a minimum vertex cover. So this, taking those 3 vertices would be minimal in the sense that, okay, if I drop any vertex, some edge will become uncovered. But as we already pointed out, you should take those 2 vertices instead. That would be minimum. Okay. Oh, I guess to drill the point, I made another example. So a more exaggerated example, if you took all these vertices on the outside, that would be minimal and very far from minimum. Okay, so this is different than spanning trees. Simple greedy algorithms won't work. Okay, the other problem is matching. We've already talked about bipartite matching, so we're going to remove the bipartite part. So in general, a matching is just a set of edges that are disjoint from one another. Okay, so here again is the same graph, too big to probably eyeball a solution. So the goal is to come up with a matching and take as many edges as possible so that they're disjoint. And I guess I'll just start pointing again instead of having you guys stare at it for a minute for no reason. Okay, so I'll just point to edges and you tell me if I should take it or not, and then we'll zoom out and see if it's a good solution. Okay. All right, so I'll start at the top. Would you like me to take this edge? Yes. Okay. And that means that some of these edges I definitely cannot take. So let me. Okay. All right, so as soon as I take an edge, all the incident edges, I guess there's actually more, are now out of the running. Okay, so you get the idea. All right, so I can't do that, I can't do that. Okay, how about in sort of this diagonal one? Should I take this? I see 1 yes, 2 yeses, okay. And that immediately eliminates these edges, right? They are incident to the edge we took. All right, what will come next? How about on the right, that edge? Oh, yeah? Oh, yeah, I missed some. Absolutely, yeah. Okay. But yeah, so now let's look at this edge on the right. You want me to take that edge? This is a controversial one. Okay, I see a yes. Okay, I see a thumbs up. Okay, let's take it. Okay. That eliminates a few more edges. Okay, how about that edge on the left? Yeah, okay, I see one very confident nod. Okay, for some reason. All right, so that eliminates some more edges. All right, how about that edge? Okay, we'll take that. That eliminates some more edges. Okay, this edge in the middle. Would you like me to take this one? Oh, I missed. Oh, I missed some down below too. Okay, good, good. All right, this middle edge though. Would you like me to take it? I see one yes. All right, let's take it. That will eliminate a few more edges. Hopefully, oh, and these guys as well. Okay, what's next? How about that edge? Yes, okay. Note to self, make smaller graphs. What else is left? I guess this edge is still available. Oh no, that one's gone. Oh yes, but that is marked actually, just on the other end. Okay, then how about that edge? Okay, we're doing pretty well. Okay, that eliminates a few more. Okay, what's still available? Okay, how about sort of awkward? That edge, sort of going diagonally up. One very slow head nod here, faster head nod. Okay. Eliminate a few more. What's up? I guess that edge is left. This one. Okay. All right. How did we do? Did we get a good matching? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. Does anyone see any way we can do better? Yeah. No. We want to take as many edges as possible. We can only use each vertex once. Yeah. So this is packing. Yeah.
So is that maximal then? Because if we use 10 and there's 21.
Yeah, there's 20 or 21 vertices. I wonder if I miscounted. It looks like we've matched every vertex, right? Is there any vertex we've left out? So I guess that's the best. Maybe there was 20 vertices after all. I can't count to 20, and especially if they all look the same. And we got 10 edges. So n over 2 is the best we're going to do. So okay, good job. All right, this is maybe not. If you solve all the problems, it's not as impressive when we discuss them in general. Okay, so that was another matching that was prepared. Okay, so that's the maximum matching problem. You want to choose as many edges as possible. Again, we've already done the bipartite version, so it's not too surprising. You can also ask, is there a matching of size k? All right, so I guess the same point as before. For this problem as well, maximal is not maximum. So simple greedy algorithms don't work, even though you guys figured it out. So here would be a maximal matching on the left. I've taken 2 edges, but I can't add any more. The maximum would take those kind of odd ones instead. Okay, so really straightforward greedy algorithms won't necessarily work because it gets stuck at a maximal matching. That's not a maximum matching. Okay. All right. I guess I gave you guys one more puzzle. Here's a graph with 16 vertices. This one has a little bit more symmetry. And I guess I was going to ask you, you guys still have the energy, what is the size of the maximum matching in this graph? One person just gave me a no. Okay, yeah.
Okay, so I believe if you take that edge that goes like downwards and to the right at a 45-degree angle, and then every single edge that goes like upwards and to the right at a 45-degree angle, just take all those edges. That's the number. Yeah, so that one.
Okay. Yeah, okay, so this one was more planted. I tried to give an example where it's easier to see that's a maximum matching. Okay, fine. When you're able to kind of hit all the vertices, so you really get n over 2 exactly, sometimes that's called a perfect matching, because it's the best you can do. Not all graphs have perfect matchings, but some do. Okay, so this is another example of packing and covering duality. So in matchings, I'm packing edges into the endpoints, so I can only take one edge for each vertex. And for the covering side, I'm trying to cover all the edges with vertices, where vertex covers kind of all the edges is incident to it. Okay, so this is the same as sort of forest versus spanning sets. This is the same as packing paths versus cuts. Okay, so there's some similarity going on here. Okay, so that means basically for free from the incidence structure, we'll go through it together. But we're going to show that any matching, however many edges you find, is smaller than any vertex cover, how many vertices you find in a vertex cover. Packing is less than equal to covering in any of these incidence problems. Okay, but we'll prove it just for this special case. Okay, so I want to show that you give me any matching in any vertex cover, the number of edges in the matching is the most number of vertices in the vertex cover. Okay, so let's let M be a matching, let S be a vertex cover. Okay, now left one part blank. All right. Every edge in our matching has at least blankety blank endpoints in our vertex cover. What goes in the square? Yeah. 1, because S is a vertex cover. So because S is a vertex cover, it's going to have at least one of the endpoints of every edge. Okay, so this is leveraging our definition of a vertex cover. So because S is a vertex cover, for any edge in our matching, I'm going to have at least one endpoint. Okay. On the other hand, because M is a matching, I know that the endpoints of all the edges are so the definition of a matching is what? I have two edges in a matching. What do I know about the endpoints? Can they be the same? Can they not? They always have to be different. They're always distinct. Okay. Okay, so what does that mean? So for every edge, I can find some vertex in a vertex covering, right? But I was only worried about like, oh, is the edge choosing the same, or two edges choosing the same edge in a vertex covering? No, they're choosing different ones because the endpoints are all distinct. Okay, so we sort of have an injective matching where for each matching, I choose one endpoint that's in the vertex cover, and that's one-to-one. Okay. So we conclude that the number of vertices in our vertex cover is at least the number of edges in our matching. Okay, for each edge, I can pick a vertex, and those are all different vertices that are picked. Okay, so so now we've established that we have this less than equal to, which is always true of packing and covering problems. The question now is, are they equal or greater than equal or something? Okay, so for both spanning trees and for ST flows and cuts, we're able to show that the packing problem was always equal to the covering problem. That was super useful, right? This max flow min cut theorem was super useful for all these applications and all these arguments. Okay, so what about this one? I'll take a poll. Yes, they're always equal, or no, they're not always equal. Okay, the question makes sense? You don't know if they're equal or not. Okay. Who thinks we can show that the size of a maximum matching is always equal to the size of a minimum vertex cover? Okay, just three. Oh, one sec. Who's not voting? Okay. Okay, who thinks that they're not necessarily equal? Okay. Looks like very high honesty rate. Okay. Okay, most people thought that they might not be equal. Who can think of then a counterexample or some simple graph where the size at a maximum matching does not equal the size of a minimum vertex cover? Yeah. Oh, okay. I guess that's even simpler than I thought. Okay. I suppose if there's one vertex, but this might be 0 and 0 because I don't actually have to take the vertex because I don't have to cover any edges. Okay, so so there's no counterexample with one or fewer vertices then. Anyone think of a bigger graph? Yeah.
Just a line with an odd number of vertices.
A line with an odd number of vertices. So this is 3. And then there is... Okay, so any matching has only one edge. But here's my vertex cover of size 1. Okay. Yeah.
What if you make a vertex or an edge from the left vertex to the right one?
Okay, so you're describing a triangle. So you're very close. Okay. In a triangle, we can only take one of the edges. Okay. But then any vertex cover has to take at least 2 corners of the triangle. Okay, so here the minimum vertex cover is 2, the maximum matching is 1. So that's an example where they're not necessarily equal. That's different than any of the problems we've discussed so far. Okay, so having established these preliminaries, I wanted to ask my favorite question. So we have 2 problems in 2 categories, vertex cover and matchings, and whether we're going to be able to get a polynomial time algorithm or find out that it can solve all the world's ills, and therefore it's probably NP hard. Okay. So there's vertex cover and there's matchings, and then I should make one more category for no vote. Okay, so very quickly, who's not going to vote? Okay, more people are not going to vote than last time. As enthusiasm wanes. Okay. Okay, so let's start with who thinks we can get a polynomial time algorithm for vertex cover? Okay, that's like 20%-ish, which is about half of the people who are going to vote, I think. And who thinks that vertex cover is going to turn out to be hard? Well, actually, that looks like more. Okay, so maybe that's like 58%. Okay. All right. Who thinks we'll get a polynomial time algorithm for matchings? Okay, roughly a similar number, but maybe that's actually less. I don't know. And then who thinks it'll turn out to be NP hard? Oh, okay. This doesn't quite add up, but that's fine. Okay. Okay. All right. So, fairly thick mixed opinions on these problems. Okay. Pretty close to balanced. All right. So, vertex cover turns out to be NP hard. So, congratulations, 58% of the class. And we're going to do a reduction for an independent set. It's actually going to be pretty quick. So, those are the same graphs. So let's pick here I'm just circling an independent set of vertices. I think it's the biggest one, but who knows? Okay, so I've highlighted in yellow an independent set in the graph. Okay. Now look at all the vertices that are left out. Here highlighted in teal. There's something conspicuous about that vertex set highlighted in teal. Yeah, it's a vertex cover. Okay, which makes total sense. So independent set means I can't take both endpoints of any edge. So I have to leave out at least one endpoint. Okay, whatever is left out covers that edge. Okay. So for any independent set, the complementary set is always a vertex cover. For every vertex cover, the complementary set is independent. So a vertex cover has to take at least one vertex from every edge. So the complement can't have both vertices. Okay. So that means that maximizing the size of the independent set is really the same thing as minimizing the size of the vertex cover by just taking the complement. Yeah.
For the minimum vertex cover problem,
Yeah.
it seems very similar to minimum dominating set problem. It almost seems like the same. Like I feel like
Sure. Okay, so dominating set means that, do you remember the definition of dominating set?
Yeah, it's like every single vertex in the dominating, or every single vertex in the graph either has to be in the dominating set or adjacent to a vertex in the dominating set. Right?
Yeah, so that's right. So dominating set says that it's sort of like vertices covering vertices. Okay, so I have to make sure that for every vertex in a graph, I either take that vertex or some neighbor of that vertex. Whereas vertex cover is covering the edges of the graph. Let's see if I can find, okay, let's see. Okay, so I think that in this graph in teal, I think that is the minimum vertex cover. So I guess my question is there a smaller dominating set? I don't think there is. Okay, so that's not a good example. Okay, so here, if you go to our triangle, So we know that our vertex cover needed 2. But what's the minimum dominating set in a triangle? It would be 1. Just one corner covers everything. So there is a slight difference. They do both turn out to be hard. They're actually different. You can actually, so sometimes when you do, when a problem's NP hard, you can't solve it exactly, so you might try to approximate. You can get a 1/2 approximation for vertex cover, and I think you can only get a logarithmic approximation for dominating set. So in some sense, vertex cover is easier from the approximate point of view, but it doesn't matter. I was trying to give another example of the difference between the two problems. Okay. All right. That does also suggest maybe this would have been a good homework problem or something. Instead of reducing to and from independent set, I wonder if you can go between vertex cover and dominating set given sort of the similarity in character. Okay, but it's too late for homework, at least before this midterm. Okay, so, all right, so that resolves the vertex cover question. Let's move on to maximum matchings. The question is whether it's hard or easy. I tried to list maybe some arguments why it might be hard, why it might be easy. I don't know if they're very helpful. So one thing is that we've been talking a lot about sort of how the primal and dual problem are often closely related to each other. They're two sides of the same coin sometimes. And here we've shown that the dual problem is NP hard. Right? So at some level, there's some kind of mirror image thing going on between vertex cover and matchings, and we've shown that vertex cover is NP hard. Maybe that suggests maximum matching is NP hard. I would say maybe the best argument on the easy side is that I do know how to solve the bipartite version of the problem. We did that before spring break. Okay. Now, maybe you're wondering how come we haven't already shown it's hard. Okay, so in other words, does getting can I use minimum vertex cover to figure out the size of the maximum matching, right? Or no, vice versa. Vice versa. Okay, so let me rephrase. Although vertex cover is the dual problem, and we've shown it to be NP hard, it doesn't actually imply that primal problem matching is NP hard, and the question is why? Yeah. Because equality is not strict. So if the equality was strict, if we did actually show that the maximum matching was always equal to the minimum vertex cover, then by finding the maximum matching, I could identify the minimum vertex cover. But in fact, we didn't show it to be true. So there is a slight kind of decoupling there, which at least allows for the possibility of some different outcomes. That also is unusual based on our discussions. Okay, I don't know if the last argument is very useful. Finding a maximal matching is easy. I feel like that can be a pro or a con, but anyway. Okay. All right, so remember this example from before, which had a sort of a planted. So here I've highlighted, okay, we're going to start analyzing things. So here I've highlighted a maximal matching in that example graph and a maximum matching in the example graph. Okay. And, okay. Now, okay. So what I want to do is look at the difference in size between a maximal matching and a maximum matching. So I know that, of course, a maximum matching has at least as many edges as a maximal matching because that's what maximum means. Okay. I guess the question is whether there is some kind of converse relationship. So, is it possible that any maximal matching is at least 1% of any maximum matching, or maybe square root of a maximum matching? Is there any connection? What is the most exaggerated difference I can think of between a maximal matching and a maximum matching? It's a reasonable question to ask just to open up the problem, right? Because maximal matchings we can't compute. We don't know how to get maximum matchings. We can always see if there's a big difference. Okay. Okay. So we're gonna try to answer this question. So let's say that for simplicity, the maximal matching and the maximum matching are disjoint. Otherwise, you just kind of take the common edges, throw it away, and then just analyze the disjoint parts. Right? I'm trying to compare their sizes. Okay. So now out of the original graph, let me drop all the edges that aren't among the two sets. Okay, so here I've only left the blue and the red, so it looks a little less cluttered. Okay. Now, when I look at this graph, which of course is cleaned up, there's something unusual about it. I guess there's probably many things unusual about it. Nonetheless, I'm asking, what are some things about this graph that make it maybe a little simpler or more restricted than any other graph? Yeah.
If you take the path from like the I guess like kind of the leftmost like the one above the leftmost, start at the beginning there, and then you just take the path all the way up to the one kind of on the top right that also doesn't like could kind of be like the point of the whole thing. Then it alternates from red to blue.
Okay, so there's these long paths, and these are all like forced, right? So as I traced that, I didn't have any real choices to make. They also alternated red and blue. Okay, so one thing going on is that the maximum degree in this graph is at most 2. Okay, because of course for any vertex I can take at most one red edge and one blue edge, because red can only have one edge incident to a vertex. Blue can only have one edge incident to a vertex. So if I take the union of two matchings, I always get a degree 2 graph. Okay. And it's always going to be alternating colors as you walk around the path. So a degree 2 graph can always be decomposed into paths and cycles. On one hand, I can just pick one vertex that has degree 1 and just start walking around, right? And at some point it's going to end. And when it ends, it'll be a path. Okay. But I can also, it doesn't have to be degree 1. I can start walking around from this vertex. And when I finish, it'll be a cycle. Or it could have split off at 2 paths. Okay. So any maximum degree 2 graph can be broken down into cycles and paths. Okay. All right, so, okay. This was supposed to just be examples. Okay, so the graph will always decompose into paths and cycles because the degree is at most 2, and also it's going to be kind of alternating colors along the cycle or along the path. Okay, just from the fact that we're combining two matchings. Okay. All right, so again, I'm still interested in this question of how big or what is the difference in size in the extreme case between a maximal matching and a maximum matching. So let's look at a cycle induced by, found in the combination of a maximal matching and a maximum matching. How does the number of edges in the maximal matching compare to the number of edges in the maximum matching? They're equal. They have to be equal. It has to be an even length cycle. It's going red, blue, red, blue, red, blue. So you always end up with as many reds as blue. Okay. All right, now what about paths? Okay. So first of all, I'll suggest that if I look at any path, the number of edges in our maximum matching has to be at least the number of edges in the maximal matching, but why? Yeah.
I don't know if this is the full answer, but because we know that the inequality exists, if the cycles are equal, then these can be equal, otherwise it's strict equality. Like they'd be the exact same size.
So it is possible to have so in this picture, it starts with red and ends with red, but it could have ended with blue. You know, if I just leave out this last edge, we'd have an even length path. So it could be equal.
It could, but there must exist a path that's not equal, otherwise, or a path that could be not equal, otherwise, a maximal and maximum.
Oh, okay. Well, a maximal is allowed to be a maximum.
Yeah.
Yeah, so there should be one that's not equal. But okay, but I guess I'm asking first. I think you're anticipating the next slide. But this part is just why. Yeah.
So if you took away all the other edges, then it would be a contradiction that the maximum was actually maximum.
Yeah. Okay. So there's so in particular, let's say that okay, let's say I erase two edges, or I'll okay. So let's say I sort of ignore those two. Oh, interesting. There's blue behind it. That's not right. Okay. Let's say I erase these two edges. Okay. So this would be, I had claimed that red is a maximum matching, but now there are three blue edges in a maximal matching and two red edges from the maximum matching. I'm saying this is a thing that's not supposed to be able to happen. So yeah, so where is this a contradiction?
Well, if you only consider the graph of those edges, then the maximal would be actually maximum wouldn't be.
That's true, although I guess I don't know if maximum is necessarily required kind of to be maximum over all subgraphs. But I think you're very close to something, which is that if I had this kind of arrangement, I can switch color. I mean, I can add all the blue edges to my red set and drop out those red edges. Okay, so I can kind of, erase these two and make these red. Okay, and I would have still a matching because there's no other incident edges out there. Okay, so I can actually swap along alternating paths. So if there was more blue edges than red, I could have increased the size of the red, which we're not supposed to be able to do if red is really as big as possible. Okay, so that's one side. But now I'm interested in the other side of the inequality. I want to argue that in any alternating path, the number of blue edges has to be bigger than some factor times the number of red edges. Yeah.
You're saying in any one path?
In any one path.
Like one less than.
Yeah, it's always greater than or equal to this minus 1 or something, because it's going red, blue, red, blue, red, blue. So in the worst case, maybe the outer ones are red, the inner ones are blue. So you end up with one more red than blue. Okay. But the shortest path that can have red and blues in it has length 3. So okay, you have in which case it would be 2v1. So it's always at least 1/2. Okay, so alright, so what does that all mean? Okay, so the worst case looks like that. Okay, so we've shown that for any cycle, did I get that backwards? I got that backwards. Okay, the number of edges in the maximum matching is equal to the number of edges in the maximum matching. But for paths, I know that the number of edges in the maximum matching is at least 1/2 the number of edges in any maximum matching. Okay, so if I put everything together, then we always get that, maximum, of course, is bigger than maximal, but we've also shown that maximal is at least 1/2 of maximum. Okay. So this is also a little different than anything we've seen before. So when we did ST paths, I think we had example, we knew that maximal could be really far away from maximum because of that example was the middle edge, I guess from your point of view, like that. But here we're always within a factor of 1/2. Okay, so, all right, so maybe revising, going back to this question, is finding a maximum matching NP hard? We have one more observation is that, okay, maybe maximal matchings aren't necessarily maximum, but they always get you at least 50% of a maximum matching. Okay. I don't know if that helps or hurts the argument. Okay, that's interesting. Okay, so, all right, let's start trying to make an algorithm for matchings. All right, so, okay, what did we just discuss? Okay, if you take any maximal matching, any maximum matching, it's going to decompose into disjoint paths and cycles. Okay. And at this critical point here, we pointed out that in any of these paths that are induced by the combination of the two matchings, the number of matchings in the maximum, number of edges in the maximum matching has to be at least the number of edges in the non-maximum matching, because otherwise we could have exchanged along the path and made our quote-unquote maximum matching bigger, which you're not supposed to be able to do. It's maximum. Okay. All right, so that suggests, an idea that's very familiar to us. So let's say that, okay, here's a very simple graph with two edges in my matching highlighted in red. Okay, but of course not the maximum. The maximum is 3 taking the outer edges. Right, and so algorithmically, how might I be able to find one of these augmenting paths? Right, so at the endpoints we have these sort of free vertices, free in the sense that they're not yet matched by any edge. Right, and then maybe we can just run BFS or something, walk along this, and finding alternating path going black, red, or unmatched, match, unmatched, matched, unmatched, free vertex, and then we can make an exchange, right? So we can try to look for a path from one unmatched edge to another unmatched edge, one unmatched vertex to another unmatched vertex. That's alternating, right, between unmatched edges and matched edges. Okay. And if we find one, then I can swap them. I can swap all the red for the black and increase the size of my matching. Okay. All right, so you do something like this, you do the exchange, okay, you've added one more edge to your matching. Okay, so it's very similar to some of the flow algorithms and disjoint path algorithms we've discussed. Okay. Now, suppose you look for a path and you conclude there aren't any. Then what? Suppose I have a matching, I don't know if it's a maximum matching, but I did look for an augmenting path, I didn't find any. What can I say? Yeah. It's the maximum because, okay, so, at some level we're sitting at, I think I got this backwards again. Okay, so, we're just a blue set right now, right? In the sense that we don't know for a maximum. But if I compared myself to a maximum in the analysis, I don't know the true maximum. I would be able to decompose the combination of my matching, whatever is truly the best matching, to paths and cycles. Okay? But the fact that there's no augmenting path means that there's no kind of path in this decomposition that's going maximum, then me, then maximum. an ending, because that would give me an augmenting path. Okay, so we're already kind of tying the maximum matching on all cycles in that decomposition, but no augmenting path means that I'm also kind of tying on all of the paths in the decomposition. Okay, so it's never going red, blue, red, blue, red, and ending there, because that would be an example of an augmenting path originally. Okay, so that means any of these paths in decomposition have to go like red, blue, like that, and you're tying. Okay, so if there's no augmenting paths, then you have a maximum matching. Okay. All right, so that's just an algorithm like this, very similar to other algorithms we've done. Okay, we start with empty matching, and until I can't find any more augmenting paths, I look for an augmenting path and I make an exchange. Okay. All right, so there is this looks simple, but there's one sort of unanswered question, which is how do I find an augmenting path? How do I find an augmenting path? So let's first, since we're familiar with this, what would I have done in a bipartite graph? Now we've already shown you can reduce the from bipartite to flow and stuff, so you can try to reverse engineer what you would have done. Okay. In the bipartite case, I've circled a free vertex that I would like to find an augmenting path for. Does anyone see an augmenting path for this vertex? Yeah. Okay. Yeah. Should I go up or down then? Okay, we'll go up. Okay. We only have one choice. Okay. Top one or bottom one? I guess we have two choices. Or the middle one or the bottom? Okay, one sec. So we're here, right, in the top left? Okay, so should I take, there's two blue edges. Which one should I take? The higher one or the lower? Okay. And then I have to take oops. Then we have to take this red edge. Okay, and then what's the last edge? I guess this. Okay, so you can find an augmenting path like that, in this example. But I guess the question is, algorithmically, how would you have automated this search? And how would Ford Fulkerson have done it if we reverse engineer? Yeah.
Something I see about this augmenting path is that the start and the end point both only have blue edges coming from the vertices. Maybe something along those lines.
Yes, okay, so if we remember, okay, so our construction for bipartite matching, we added a super source and a super sink, right? And we would start trying to match things. Now, one thing that's important is that initially, when we had no edges in our matching, everything was directed from left to right in that reduction. Okay. And when I took matchings, what's happening in the residual graph is we're adding edges in the reverse direction. That's what Ford Fulkerson is doing in the residual graph. Okay, so the residual graph would look like this, right? And you would start here, and then you could run BFS or something and try to get to the end. Okay, I think this is actually a little bit, the matched vertices would have reverse direction, so that's not a perfect picture. Okay, so, but the key point is that to automate the search, I would want to direct the unmatched direct edges in one direction and the matched edges in the other. That'll prevent me from, in my search algorithm, going unmatched, unmatched. So by choosing directions, I can force the path I find to be alternating. Alright, so fine. The directions will let us do alternating paths. What about general graphs? Okay. What if I wanted to find an augmenting path, but the graph was not necessarily bipartite? Yeah.
Could you create a copy of the graph and send the blue edges from graph 2 and then the red ones from graph 2 to graph 1, and then you force it into a bipartite?
Okay, so you want to duplicate the edges to make kind of a bipartite graph and go left to right, left to right?
Yeah, it's like the blue ones would go left to right and the red ones would go right to left.
Okay, so sorry, yes, okay. Okay, so I guess I can do that. Or I can. Damn it. Okay, so this is sort of kind of, you want to kind of duplicate this, and then sort of red edges should go that way, and sort of blue edges should go that way, so to speak, corresponding to the appropriate copies. Now, one issue though is that, and there may be some auxiliary supersort supersync, is that a path in this duplicated graph won't necessarily give you a path in the original graph. Because you may use vertex A on the left side and vertex A on the right side in your path in this bipartite graph. So it won't necessarily give you an augmenting path in the original graph, although there will be some kind of red blueness going on. Okay, so at the very least, it's not clear how to orient the edges. This is a reasonable idea, but it's not perfect. And in general, it's not clear. We don't have as easy a trick as just orienting the edges as we did for bipartite graph, where there's a very clear left and right we can work with. Okay, so what's something you might still go ahead and try to just say, whatever. I'm just going to do DFS anyway. I'm going to hard code my breadth first search or depth first search to alternate between blue, red, something like that, right? And this may happen also for your approach implicitly. Okay, so what can happen? I could start at this vertex here, and start walking around this way. So I take a blue edge first. My algorithm knows I should take a red edge next. Okay. Then I should take a blue edge. Then I should take a red edge. Then I should take a blue edge. Okay. And if I had to take a red edge, then I would go back to here probably. Well, you've kind of already taken it in the other direction. A blue edge kind of going back to here or something. But the point is, your search kind of got stuck. Okay. All right, so what happened though? What's so weird and sort of something that's sort of new is that we have an odd cycle. Okay? So we find an odd cycle in the graph that went blue, red, blue. Okay, which just hadn't come up in any of our discussions before. Okay, all right, the best I can do. I'm not going to sing the song. You guys all hear it in your head. Okay, so these search approaches, the issue is these straightforward search approaches kind of inspired by Ford Fulkerson and inspired by disjoint paths, is that we stumble into these odd alternating cycles, which don't really make sense because we end up with blue stuff. Okay, so this is called, by the people who worked on this, it's called a blossom, I guess. And maybe one thing kind of interesting to point out, in a bipartite graph, this could never happen. There's no odd cycles in a bipartite graph, right? Because even or odd, even to start and end the same place, you have to take an even number of edges. You're bouncing back and forth. Okay, so just some terminology. Okay, I don't know if it's more historical. So okay, so to define kind of what happened. Okay, so I started at a free vertex. I start walking around, right? And I first take blue red, blue red, blue red, and then I enter the odd cycle. And then so the first part is a path, and then we have an odd cycle for the rest, running into somewhere we've already been. And this first part, I guess what people call it, this is sometimes called the stem of the flower, the beginning. This odd cycle is called the blossom. And then this particular junction point is called the base. I don't know if it's very useful vocabulary, but that's the historical nomenclature. Okay, so what are we going to do? So we are going to try to extend this idea, but you do this search, red, blue, red, blue, red, blue, and you find a blossom. Okay, and the question is, what can I do? Okay, what can I do with this odd cycle here in particular? Okay, so here then is the sort of incredibly bold idea by Jack Edmonds. This is 1963. He'll take this blossom, and what he did was he said, I'm going to contract this to a single vertex. He sort of makes a new graph where the blossom is contracted to a single vertex. Okay, I think it's drawn here. Okay, so this would be the graph that remains after contracting the blossom to a single vertex. Now suppose I ran another search in this graph. Okay, so I'm starting at this free vertex again. And I walk around, okay? And I enter the blossom on a red edge, or the vertex that contracted the blossom. Okay, so my last edge was red, so I can only escape through a blue edge. So for example, I can go like that. Okay. So in this different graph, in this contracted graph, we were able to find an alternating path. Right? Okay, good. So you find an odd cycle, he contracted them. And then keeps looking for a path, and let's say we find it in the next iteration, otherwise maybe you keep contracting more blossoms. Okay, so you have something like this, right? And now, okay, so we want to argue that, I should have erased this. Okay. All right, so if I uncontract the blossom and look at the original graph, then here's sort of the two paths we made plus this void in the middle from uncontracting the blossom. Okay. And I want to argue that I can still find I can kind of fix this. Okay, but how can I fix this? I sort of have the beginning and end of a path. Yeah. Okay, so I can take the bottom half. Okay. So in particular, in the blossom, I need to find a path that has an even number of edges, because then it'll go, because I entered the blossom at blue, blue. So it'll go blue, red, blue, red, blue, red. Okay. And so I can exit the blossom, and one of the two sides will always work. If it wasn't down and the parity was off, then I would have taken the upper part. Okay, because it's odd, so one of the two are going to give you the right parity. Okay, so I guess here I drew another example, hoping that would be more compelling. So here then is another augmenting path with the blossom contracted. Okay, and so for this one you would want to go up. Okay. Going down wouldn't have worked because you needed the last edge to be red. All right, so those are some nice pictures. Okay, so then here are the two kind of if and only ifs. Suppose I already have some matching, and I find a blossom with respect to the matching. Okay, and I let G prime and M prime be the contracted blossom and matching. It's worth pointing out that in this, do I have any pictures left? The blossom, no, okay. Okay, so if I look here, I should point out that, out of this blossom, right, out of this odd cycle, there's only one red edge incident to the cycle. There's red edges in the cycle, okay, but because everywhere else along the blossom is going red, blue, red, blue, red, blue, I cannot possibly have another red edge, another matched edge like that or something, because that would have given me two matched edges in a row. Okay, so I always had to enter the blossom on a matched edge, and it had to split up into two unmatched edges, and the rest goes red, blue, red, blue, red, blue. So all the other edges that hang off of the blossom, they're always blue. They're always unmatched. Okay, so that's important to point out. So in particular, when I contract the matching, the blossom, in some of that also kind of collapses my matching in the contracted graph. You'll still have a matching. You won't create any incidences because there's only one edge sort of entering the blossom. Okay, so if you have an augmenting path in this contracted graph, you can always lift it to an augmenting path in the original graph. Okay. And vice versa, any augmenting path in the original graph, you can contract it because you're entering a red edge and leaving a blue edge. And you'll get an augmenting path in the contracted graph. Okay, so you'll get this one-to-one relationship between augmenting paths in the original graph. It's not one-to-one, but whatever. You'll preserve augmenting paths. And you'll be able to lift the augmenting path back out when you uncontract the blossom to try to find the path in the original graph. Okay, so in my example, there's only one blossom and then we found it, but you could be finding lots of blossoms, in which case you have to back out a lot to get the original augmenting path. Okay. All right, so one thing sort of interesting, I guess this is not really a proof, but more just watching things work out. So here, for example, is an augmenting path in the bottom right? That's actually not using the stem of the blossom. Okay, so the claim is just that if there's an augmenting path in the original graph, you can get an augmenting path back out. Now, what's interesting, if I contract this blossom, okay, then what's left here, right, is actually not an augmenting path in the contracted graph because it's going kind of blue, blue in the middle now. Okay, but my claim is just that there is an augmenting path somewhere. Okay, so there's still, of course, an augmenting path in the graph because I know that every blossom had a stem, to use their words. So some kind of path starting from a free vertex that enters on a matched edge. Okay, so instead of using that augmenting path down below, I am promised that I can find a different augmenting path using the stem. So I'll still find a augmenting path. Okay. All All right, so I guess I'll try to wrap up. Okay, so this is this very famous Blossom algorithm. It's an augmenting path algorithm by Jack Edmonds. And it's still really an augmenting path algorithm like before, but it adds this ingredient of a blossom. So you look for an augmenting path, red, blue, red, blue, red, blue, red, blue, but you might find yourself completing a cycle. Okay, but when that happens, that means you found the blossom. Okay, so you either find an augmenting path, you successfully make your way to another free vertex, or you find a blossom and you shrink it, and you repeat. Okay? Or if you do find an augmenting path, by then you've shrunk a lot of blossoms, so you have to expand them back out and figure out if you go up or down around the blossom to repair it one at a time. Okay, so you may have to undo lots of blossoms. Okay. All right, but it'll work. Okay. All right, what is the running time of this algorithm? So each time when I do red, blue, red, blue, red, blue, we can basically do the copying, two copies of the graph to force ourselves to alternate, but keep track of when you're sort of visiting the same vertex twice, sort of in the original graph. Okay, so that's one BFS. So you should only need linear time to find one of these blossoms. Okay. Now you're going to keep finding blossoms until you eventually get an augmenting path. What's the biggest, how many blossoms can I run into? Yeah, find a blossom, contract, find a blossom, contract, find a blossom, contract. Eventually there's going to be like no vertices left if I keep contracting. Right? Each time I'm taking at least 3 vertices and shrinking it into 1. Okay. So that means I can only contract like at most n or so blossoms before there's so few vertices we must have run out and either found a path, or if we didn't, then we have a maximum matching. Okay. And how many paths might I take? What's the maximum number of paths until I must have a maximum matching? What's the maximum size of matching? Each augmenting path will add 1 edge, so yeah, n over 2. Okay, so we put this all together, and you get an mn squared time algorithm for maximum matching. It turns out we have a polynomial time algorithm for maximum matching, even though vertex cover was NPR. Okay, so I'm going to conclude with a few historical notes. So this was a very important algorithm historically. So this paper is from 1963, which is probably one of the older ones. So I think Ford Fulkerson already existed. They already knew how to do bipartite matching. Okay, but still, this is 9 years before all the P versus NP stuff come out. So the terminology P versus NP isn't out there yet. Okay, it's actually 10 years before the C programming language. So this is really when theory was theory, because you couldn't program anything useful. That was vacuum tubes or something, or Fortran. Okay, so what's interesting is that mathematicians had already studied the matching problem, already knew that there's a finite algorithm for it because there's only finite MA edge sets. Right? So they had exponential time algorithms for matchings at the time, but it's not very compelling. In fact, I believe that sort of somebody had vaguely suggested augmenting path algorithm, but didn't realize the bug that you could run into an odd cycle. Okay? And so what's interesting, this is a major problem to solve, but what's also interesting, it's so early on that Jack Edmonds includes, section 2, the philosophical digression on the meaning of efficient algorithm. Right? So this again was before polynomial time was considered interesting. What's going on? Later he does weighted, that's also important, but okay, so here. There's an obvious finite algorithm, but that algorithm increases in difficulty exponentially with the size of the graph, so I guess you can just enumerate all possibilities. It is by no means obvious whether or not there exists an algorithm whose difficulty increases only algebraically with the size of the graph. Algebraic was, I guess, the 1960s word for polynomial. Okay. The mathematical significance of this paper rests largely on the assumption that the 2 preceding sentences have mathematical meaning. right? So he's trying to convince mathematicians to take computer science, to take algorithms seriously. He's saying, look, the existence of a polynomial time algorithm is an interesting thing, as compared to just any old finite algorithm, and that there's a difference between it. So he's anticipating the P versus NP stuff before it's really made clear by the Cook-Levin theorem and Karp's reductions. Okay, he's saying, okay, there's something important, kind of existentially important about coming up with a polynomial time algorithm. This is the same Edmonds from the Karp-Edmonds who do max flow later. See, when the measure of problem size is reasonable and when the size of assumed value is arbitrarily large, an asymptotic estimate of the running time is theoretically important. Okay, so he's saying, okay, let's not worry too much about constants. Okay, so this is, for practical purposes, the differences between polynomial and exponential running times is often more crucial than difference between finite and non-finite. Okay, so this is important. He wrote n to the fourth because he just assumed that the graph has at most n squared edges. So we did mn squared because we cared about number of edges, but he didn't. One interesting question he asked, is there a polynomial time algorithm for linear programming? So this thing called the simplex algorithm already existed, but there was examples known where it takes a long time. So this was sort of a big problem. Okay, so this is a very historically significant paper as well. Sorry. That's all. All right. Thank you.